So the last speaker is Chen from the University of California, San Diego, and he's the last of the 2020 SES fellows that we are honoring today. And the title of the talk is Manifold Learning-Based Data-Driven Modeling for Biological Tissues. And this time, for good, the floor is yours.
Thank you, Stefano. It's good to meet with you in the cyberspace. And I would like to thank the organizers, especially Chen, for taking this very difficult task and allow us to share our experiences over the pandemic. I'm also honored to be considered as SES fellow and to share with you our recent studies on manifold learning-based data-driven modeling of biological tissues. As a motivation of this work, as the data science and machine learning technologies have advanced significantly, it actually allows us now to build a digital replica of the physical ones. And General Electric was the first company that tried the idea, starting from engines and some of the aerospace structures. And now these days, with further advancement in this field, it is now possible to also consider digital twins for biological systems. And here at the Center for Extreme Events Research at UCSD, we have a group of people interested in developing digital twins for musculoskeletal systems for the ideas of, for example, enhancing your body performance for athletes or for soldiers, and also for elders for prehabilitation. And so the idea is to be able to combine, for example, sensor technologies. And these days, as you know, you can actually not only get images, but also a lot of information from the images, for example, DTI and strand maps. And so there's a lot of data that provides us a lot of new information that we can now approach the problem with a slightly different paradigm. And well, as you know, traditionally, the science goes with observation and then making hypotheses and then develop a model. And the whole purpose is really for prediction. So traditionally, when you don't have that many data, you really have to have your good knowledge and good experience of the problem that you're dealing with. And then you use limited data and construct some sort of a physical models and use that for prediction. But often when you do this, you need a lot of knowledge. It's hard to go beyond your knowledge. For example, some of the conservation laws that are well recognized and they work very well, but there are some models, for example, in particular material models, they're usually not very satisfactory, and especially for very complex material systems, right? So now with tremendous amount of data, that offers us some new opportunities and to be able to handle some of the physical models that are not that satisfactory or not that well understood. And I think especially for biological systems, the material laws are typically very complex. And so the idea here, well, maybe we can then take advantage of these two approaches for the physical laws that work well, especially in certain length scales. Just use it, and the ones that are not very well understood, we can go with the data-driven techniques. And the idea is now, how do we combine these two? So this requires a new boundary variable problem, new framework. So here, as I said, taking this as an example, this skeletal muscle systems, and as you can imagine, what you wanted to know is the very high length scale response or performance. But you need, in order to be able to predict that, you need a good understanding of the material behaviors and also mechanisms, even go all the way to molecular scale, understanding how calcium release promote cross-bridging, how cross-bridging then promote the contraction of muscle fiber, and that then propagate and generate force at the mesoscale and then up to structural scale, right? And at every scale, they are very complex biology, chemistry, and physics and mechanics, and some of them are well understood, but some are not. Right? And usually when you have a problems that the interest of the problem goes across a very wide length scales, usually at the very high length scale and very low length scale, problems are actually a little bit easier and better understood. Usually the complexities are in the middle one, in the mesoscale. And so same thing, in fact, same thing here. So the idea now is to combine data into this whole prediction process. Okay, and so here I'm taking a typical example of muscle contractions, and you can look at all these are the challenges in terms of computation and mechanics. But today I'm going to focus on these three items. You know, here, especially for digital twins, even for engineering devices, the whole idea of digital twins is really not to go with the blueprint or your design sketch. It's really to go with exactly how the parts are made, right? So you really have to rely on images. And now, particularly for bio, and especially for something that is very personalized, that we wanted to develop digital twin for a particular person, has to come from images, right? And as you can see, all these images represents a tremendous complex heterogeneity and also scales in the problem. And so this presents a first challenge of this kind of a problem, right? And now you got to construct a model entirely from images. So for this, we will propose to introduce this image-based. There are some methods that allows you to solve partial differential equations without mesh, right? And so we'll go with that. Reproducing kernel particle method is one of such approach. So we'll start with that. But then the other complexities in this whole process is really the materials law. And so that, so instead of going through, and which I'm going to make some comparisons through a conventional approach where you make assumption, you construct a mathematical form of stress-strain relationship, and then you go and characterize material constants. Instead of doing that, let's just see if we can just bring the data, stress-strain data directly, and then formulate this as a new boundary variable problem, and then see how we can then combine these two techniques and get a better understanding of the mechanics of this problem. Right, so here is a typical example that you take the images at different cross sections. And so if you have methods that allows you to directly deal with pixels, then that's your model, right? So you put them, you stack them together, and that's the model. And so now you have your model is a set of pixel points, right? So one approach to be able to solve some laws that are well understood and just need to solve for the solution, that you can go with methods that requires only nodal positions. And one such example is a reproducing kernel particle method. Here, I just wanted to highlight a few things, right? So this H vector, the one in blue, contains the monomial functions, and the order n here determines the rate of conversions, determines its order of accuracy and order of completeness. Now the red one here is called a kernel function that allows you to control the smoothness of the approximation, and it turns out to be, unlike finite elements, usually when you go beyond C0 continuity, it becomes very complicated to construct the approximations. Here, as soon as you choose the kernel function to be Cn, and n is the order of continuity, you have the approximation that's to that level of continuity. And this turns out to be actually quite useful for biological materials, because the heterogeneity of the material, when you go across from one region of material to another, it's not like engineering material where you have a sharp change of material properties. Here is a smooth transition from one material to another, right? So now you can actually use this kind of approximation to represent the smooth transition of material properties. It also allows you now to have the strain, which is not discontinuous. If you do C0 finite elements, you know strain is discontinuous. This allows you to have actually a smooth transition of strain from one region to another without dealing with these discontinuities, which does not apply or not suitable for biomaterials. So now with this, then you can now take this and take the image, you introduce, if we do have a good material law, then you can then use that and to model how the stress are generated when muscle contracts, how that leads to force generation, and use that to study performance of skeletal muscles for older, younger people, for people who are having disease and things like that. Okay, so now with that, now it comes to material law, right? So here, as you can see, the stress has two parts. One is so-called passive stress. The other one is the active stress. And for engineered material, we only consider passive stress. But for biomaterials, especially for muscle type materials, there's a contraction of the material. So it is an internal motor. Now this can actually be linked to the cross-bridging mechanisms that is actually related to calcium release. And there are several models already, in fact, many models already, that allows you to use the mechanisms, the observation, and construct the active stress of muscle fibers. Now, the passive part, on the other hand, we probably thought, oh, that's probably easier, but it's actually not, because of the composition of the materials is so complex, and there have been tremendous amount of effort, right? And the most well-known YC-Fan model, to invariance-based models, to Lagrangian strength-based models, and to something called structural models. As you can see, structural models, it becomes more and more complicated. It actually can do a better job, but you see the construction of the model becomes tremendous complex. So quite often when you get to this level, then it becomes the generality. Basically what you are having here in terms of machine learning terminology is called you have a overfitting system. And so the generality of the model to different type of construction of the muscle materials may not be that great, right? So that's the issue. So here, what we are trying to do is for the physics laws that are well understood, we use them. But for the ones that are not very well understood, we go with data. And so how do we combine these two to solve problems like this? And so in the end, we also collect, of course, a lot of experimental data, and let's then make a comparison on how the prediction compares by using phenomenological law and by using this data-driven type approach. Okay, so with that, let's first define what we call the physics manifold. These are the I'm taking the simplistic model. Okay, so here just consider equilibrium, which equilibrium governs stress, and really the only unknown in the equilibrium is only stress. And boundary condition, of course, you have to have entirely Neumann type, right? Meaning the tractions are all given. But what if you have the problem where not all the boundary conditions are traction given? And then you have to go to, say, for example, in this elasticity displacement, right? So then you have to now introduce compatibility. Okay, so now this is where it becomes, the problem is not complete unless you can link from stress to strain. Then you have a complete boundary layer problem. Okay, well, for that you need traditionally the constitutive. Okay, so let me first define this physical, we call the physical manifold. Where you have two independent variables, is stress field, which satisfies equilibrium and satisfies the traction boundary condition. And then you have a displacement field, where the displacement is related to strain by compatibility. And then you have this Neumann, Dirichlet type boundary condition, where displacement is given. And then the missing link between the stress and strain, and where, by the way, strain is a function of displacement. So in this physical manifold, the independent variables are stress and displacement. Okay, now in the material set, of course, you measure all kinds of stress and strain relationship with all different kinds of testing. All right, so now the whole idea is that, well, the solution of this problem is to find the intersection of the solution from the physical manifold, C, and the material data set, E. And so how do we do that, right? So there's actually quite a bit of work being done in this area. And here I'm showing you one of the functional proposed by Kirchdorfer and Michael Ortiz is to construct, the difference or the distance between the physical stress and strain and the materials stress and strain. These are called a state. The states without heads are the physical ones. The states with head in this notation are the experimental, are the data. Okay, so basically what they propose is you define a distance function, and that measure the distance between physical state and the material state. And of course, the objective here is to find physical state that satisfy those equilibrium and compatibility, and the material state from the material data set. And that minimizes this distance function. Okay, so you can either start from looking for physical state that minimizes that function h, and the corresponding, the one that minimizes that is called j. Then you look for the material set that then minimizes j. Okay, so now with that, let's now define a function now that minimizes the distance function subjected to equilibrium and non-boundary condition, right? So the standard way is to go by Lagrange multiplier. So here you have one Lagrange multiplier for equilibrium, another Lagrange multiplier for boundary condition. And then if you take the stationary condition of that, you will then find out that one Lagrange multiplier is actually the negative of the other one. You bring it back, and then you take the first variation, which is a stationary. Then you get three sets of equations. The first equation is, you can call it a generalized equilibrium. The second set of equation, as you can see, it relates the experimental strength epsilon head to the physical strength epsilon, which is a function of displacement. The third equation that relates the experimental stress sigma head to physical stress sigma through Lagrange multiplier. All right, so now three sets of equation, you have to now introduce approximation for the three unknowns, displacements, Lagrange multiplier, and stress. Now, as I mentioned earlier, we are dealing with really pixels. And so the approximation and for biological materials is better to be smooth because of how the materials is, the properties are. So here we introduce reproducing kernel with linear basis and with smooth approximation. In this case, is C2. Now notice that for stress, it's going to be related to the experimental data. So we introduce a different approximation function, and we simply use the indicator function, which are value of 1 at the point and 0 otherwise. So if you introduce this and to the three sets of equations, the first set of equation relates experimental strength to the physical strength, which is a function of displacement. Then you do, again, keep in mind that we're dealing with pixels. So simply just do a nodal integration at a nodal point and use what we call a stabilized conformal nodal integration to evaluate the gradient, right? So keep in mind, we don't have a mesh. We have everything just a point, pixel points. So I don't want to take the direct derivative. I would like to, especially to deal with data, I'm going to exactly process on the measurement. And so if you do a contour integral along a point here, it actually gives you an approximation of a gradient. And this can be shown that even in solving a boundary variable problem, this way of computing the strength by contour integral will give you exactly exact satisfaction of linear patch test. If you pass linear patch test, you get an exact linear solution. And the second equation is the generalized equilibrium that allows you to then relate the stress to force. The third one also by collocation, because I would now like to relate the experimental stress, the data point, to physical stress through Lagrange multiplier. You can then substitute the third equation into the second one that allows you to compute the Lagrange multiplier through the experimental discrete data, stress data. Once the Lagrange multiplier is obtained, then you come back to the third equation. Now you can then use the experimental stress corrected by the Lagrange multiplier to obtain the physical stress. Okay, so now we have the global problem solved. Now we get down to the local step. So once the physical stress and strain are obtained, then you look for data that is closest, stress strain data that is closest to the physical stress and strain. Right? And the earlier work by Kirchdorfer and Ortiz is simply by the distance minimization, the one that I have introduced. Now here that works okay, but as you know, data has never been perfect. And especially for biological data, there's really a lot of noise. There are also outliers. And so with that in mind, as you can hear, here we generate some sort of a synthetic data. It's this linear stress-strain relationship, but just perturb a point here, assuming that there's an outlier or noise in the data, and for a given stress, you actually will find the wrong strand because of the noise in the data. For nonlinear curve, the same thing. For a given stress, you find the wrong strand. Ideally, it will be right here, but instead, if there's a noise, you'll be getting strand is just right here. And so this is where we introduce this manifold learning. The concept, the idea of manifold learning is to say that you could have a data that is extreme high dimension, right? And as you can imagine here, for the problem that we are dealing with, we were dealing with stress and strain data. And stress and strain for each of the stress and strain data, in general three-dimensional case, if assuming you're using the symmetric type stress and strains, then you have 6 components each. And so altogether, at each data point, you actually have 12 components. So the data lives in an extremely high dimensional space. But the theory here is to say that even for data that is in very high dimensional space, there's often a lower dimensional manifold, right? So here's an example. If you simply look at the data in general, let's say a 3-dimensional space, it looks fairly complicated, but if you really follow that manifold, then they actually live in a low dimensional manifold, right? So the thing is that this is very similar to numerical solution of a PDE, which could be in extremely high order. But when you approximate a solution, you can actually go to local and make an assumption of low order approximations. It's the same thing here, but in terms of machine learning and data science, there's some work being proposed before called a locally linear embedding theorem. And so the idea is that, well, you have data, but on the other hand, data is different from solving PDEs. Data could have noise in there. So what they did is they introduced, this is really a moving averaging of the local data, basically reconstruct for a given data point, you find its neighbor. And then you do the data reconstruction as a smoothing of the data. Now, of course, the weights applied to each data point will have to sum up to 1. And this guarantees a translational and rotational invariance of the data. Data should not be, data probably should not be affected by that. And so basically, this is a reconstruction of the data. And since it sum up to 1, it guarantees an exact representation of a constant field. And this, in terms of numerical methods, we call this actually a partition of unity, which is the very fundamental properties of all the mesh-free methods. So those properties are there actually to use. And so now, once you do this local reconstruction of the data, then you bring it back to sort of correct your data, and from there search for the closest point. So with that, now remember we have a global step where we obtain the physical state. Now coming down the local step, we bring in this idea. So for a given physical state, you define your closest neighbor, okay? And then from there, you define convex hull. So again, same idea, you take the local data points, the closest neighbor, the closest distance to the physical state, you do a local reconstruction of the data, and the data sum up to 1. And here we impose additional condition. Also, the weight has to be non-negative. So this guarantees the convexity of your local reconstructed manifold. And that is very good. In fact, that is very important to do the projection, to do this manifold projection to a lower dimensional space. It also very important for stability of the data search. Okay, so basically now you have a given stress state, given physical state, you now construct the local convex set, right? So now you basically project the physical state to the convex, to the local convex data set. So if the physical state happens to be within the convexity, within the local convex set, then that's your data set. If the physical state is outside, then basically what it gives you is the closest point projection. Okay, so now coming back to the same problem here with the outliers. So instead of finding this point for a given stress, now because of the reconstruction of the data and with bin comebacks, you'll be getting this correct strand instead of the strand that is confused by the outliers. And same thing for nonlinear stress-strain relationship. Instead of for given stress, instead of getting this strand due to the noise of the data, now you're getting the right strand. Okay, so now finally, we now use this to train the model. And here we are collecting data from 11 protocols. And so this is tissues, and is subjected to biaxial stretch for 9 protocols. There are 2 protocols that are so-called the pure shear. Pure shear is that you compress in one direction of lambda, and the other direction will be 1 over lambda. And that generally is so-called the pure stress state. Okay, and for each of the protocol, the data are collected at different stretch ratio. Okay, and so there are many data sets for each of the protocol. So there are 9 protocols on biaxial with different ratios, stretch ratios, and there are 2 protocols on pure shear. So now we take this data and we use them to characterize the material constants for 2 well-known phenomenological models. Then we try our data-driven, meaning no phenomenological law, and simply purely based on data search. Okay, so here are some comparison. In the first case, we use pure shear protocols 10 and 11 for training, right? And then for phenomenological, you will use them to characterize the constants, and then use that to see if we can then predict at least the training data. And surprisingly, as you can see, for this pure shear, the YC fun model actually does not work well for compression. Surprisingly, also same thing for the Lee and Sachs model. But for this data-driven computing, actually work quite reasonably when we compare to, okay, so the 2 on the left are the data-driven computing, and that works better than the other 4 on the right. Not only that, we also show that this locally convex data-driven approach works better than the distance minimization by Kirschdorfer and Ortiz. And so this one looks good. Now, they are not always good, right? So now here we have a more complex situation. Now we take entirely, we simply just take a biaxial test. We take 4 protocols, and they use them for training and for characterization for the phenomenological laws, and use that to predict the protocols that are not within training. Okay, so now in this case, as you can see, so the one on the left are okay, so this one, the upper left one, is the one by data-driven, and then use that to predict the behavior of the behavior that is outside of the training. And for this is within the training data, I should say interpolation. So meaning that protocol 2 and 6 are actually, although they are not the same as 1, 3, 4, 7, 8, but they are within that range. So they work well. Now for 5 and 9, that is actually 5 is outside of 1 to 4, and 9 is entirely outside of 6 to 8. Right, so for that case, then we found that for all the 3 curves, the 2 are working well, but the middle one is not as good. Now, in this case, on the other hand, the constitutive model, on the other hand, that they actually work, especially for the extrapolation case. The first and the third is also good, but the middle one appears to be better than the data-driven approach. Now, finally, we try this case that all the biaxial tension and simple and pure shear are all included in the training. So taking these 7 protocols for training that involve biaxial tension and pure shear, and then predict the other 4 protocols that are not within the training. And in this case, as you can see in the middle one, they work about the same. But on the right one, the first and third curve, in fact, especially for the third case, the data-driven one actually works better than phenomenological law. But in the middle one, actually, the phenomenological law actually works slightly better than data-driven. So there are cases where phenomenological law approaches still win, but there are other cases where data-driven actually do a better job. So in conclusion, we have introduced this hybrid data and physics models. We have introduced this new locally convex machine learning algorithm and coupled that with data-driven computing for prediction of complex material behaviors, especially for application to biological materials. And I just wanted to do a little bit of advertisements. Next year, hopefully at that time, situation will be much better. There will be an IACM conference on mechanistic machine learning and digital twins for computational science, engineering, and technology in San Diego. Okay, so with that, I conclude my talk. Thank you.
Thank you, JS, for the nice presentation, and congratulations again on your SES fellow. Let's see if there are any questions in the feed. All right, I have a question here. It says, yes, how can this modeling be applied to softening continua?
Yeah, so
and I think this is by Jargon, by the way.
Okay, for softening, in fact, even plasticity, for example, for path-dependent problems, a different approach have to be taken. History-dependent, we're actually also working on that. Apply these techniques to path-dependent problems such as plasticity, history-dependent problems, and also for softening. I think softening is actually less of the concern, unless it also involves a very strong path dependency, which it is. So really the difficulty is more on the history-dependent or path-dependent characteristics that you actually need to introduce a different. So we're actually working on a different approach for a neural net approach for that kind of a behavior. So anyway, short answer is that you have to go with a different approach.
All right, thank you. I'm checking, and I don't see any other questions. So I guess thank you, JS, for your presentation again. And I think that this brings us to the conclusion of this session.